Welcome everyone. So what we're going to be doing in this one is talking about something called reinforcement learning. This is a branch of machine learning and it's about playing games essentially. So it's making decisions. You have some brain and then that is the classical supervised learning stuff and you have to differentiate between a cat or a dog. But the next step beyond that is given your brain, you can differentiate stuff, then can you make optimal decisions? And that is what reinforcement learning is all about. So let's get straight into it. We've made some slides and we're going to talk about the cartpole problem, which is essentially the hello world of reinforcement learning. Okay, so what is it? It's learning by interaction with the environment, right? So essentially you don't know what the rules are in reinforcement learning and then you go out into the environment and discover. So for example, you are playing Atari and you don't know which boxes to shoot. So you trial and error and you discover the rules. Reinforcement learning has also been used to beat world chess champions, right? And they didn't actually know the rules, but they sort of play thousands and thousands of millions of games, right? And then they discover what the rules are, then they discover what the best way to play is. So that is reinforcement learning. I think it's awesome. So we have these agents and what we want to do is we want to make them make optimal decisions, and we have this reward function. We have this concept of reward and we want to maximize the reward. Okay, and so there's no explicit supervision. It's just essentially trial and error, and then you either get a negative reward or a positive reward or no reward. Right, and you want to maximize these rewards here. Now, the core paradigm, right? The core thing about reinforcement learning is you've got a state, action, reward, then the next state. It starts all over again. So let me just explain that a little bit, right? Now, you start at some state. Say maybe, okay, pretend you're in a pond and you need to get to the end of the pond essentially. Now you're somewhere in the pond, which is your state. Then, given your state, you decide to take an action, right? Now, depending on whatever action you take, you'll get some reward. And then you'll have this reward, it'll either be positive or negative, and we'll just save that and we'll keep it so we can learn from our mistakes. That's how we learn from the rewards. And then we will go to the next state. And repeat the cycle again. So that's about it. Now here is sort of all this stuff here in sort of mathematical terms, right? We've got the agent, the decision maker, the frog in the pond world, the environment, which is the pond, the state, which is just where you are in the pond, right? The action is if you want to jump left or right, front, back, or whatever, right? That's the set of actions. Reward. Now this is defined by the environment. So you make an environment and then you choose to get whatever reward you want. So it could be +1 for the frog, it could be -1 or 0 or something. Now, this interesting little symbol here, pi, this is pi, right? It is a policy. Now, what a policy is it's a map telling us if you're in this state, what action to take. And so over time, you would adjust your policy to take optimal actions given your states. That's the whole point of reinforcement learning. You want to get these really, really, really good policies so you can know what to do in certain situations. Okay, so what we're going to do now is tackle the cartpole problem. The cartpole problem, it's sometimes called the inverted pendulum problem, right? And so this is it. You can see right here. What we have to do is we have to move left or right and try to balance this pole upright. Yeah, so actually just try this on maybe a piece of paper or something. It's actually quite a tricky thing to do. But we can solve this with reinforcement learning. It's the hello world of reinforcement learning, essentially. Now, let's get into it. So we're going to define our environment and the actions we take, right? So the cart, right? It can be in position it can be in the position -8 to -4.8 to 4.8, sorry. So what that means is this is the cart, right? And then at the left, it'll be -4.8 and at the right it'll be 4.8, and the cart can move like this essentially. That's what that is saying. And then the cart velocity is like how quick is it going? Easy, nothing too quick. The pole angle, so the pole angle, right? So this is 0, and then it can dip this way, or it can dip that way, right? So that's the pole angle. And the angular velocity, the pole angular velocity. So how quickly it's falling, essentially, because it's not straight velocity. It's going in a circle, right? So it's angular. Anyway, so push to the right. So push to the left. Sorry. So imagine if the cart pole goes this way, you essentially want to push it that way to like rebalance it. And so we a push to the left is one move, one action we can take, and then obviously the other way is, you know, push to the right. So you want to go the other way. Okay, cool. And so the reward structure, this is very important. It's actually very important to engineer our rewards so that we get optimal policies and we can actually solve the problem. So so what we're going to do is we're going to give +1 reward every time step the pole remains upright. So we discretize our time into time steps, right? And then for every time step this thing is upright, we give it a +1 reward. But if it's like this and bang, it's dead. It's dead, right? So that'll be a 0 reward. So the episodes terminate when the angle of the pole is ±12. Fair enough. That makes sense. And then the cart pole position is going to be 2.4, right? Is ±2.4. So if we move it to the left or right too much, that means that's it. That's the end of the episode. And the episode length is going to be 500 timestamps. So that means, if you think about it, right, the maximum reward for this would be 500. So that is our optimal goal, essentially. We want to get 500 reward if every time step we get a +1 reward, right? So why the cartpole problem? This is just a bit of philosophy. It's simple, easy to visualize, and it's really the hello world of reinforcement learning. One thing also I noticed about the cartpole problem is that it doesn't actually take a lot of computing power to solve this problem. So, for example, if you know about Atari, which is a game where you could have Pac-Man or like spaceships or whatever, right? Now, with those, you can solve those with reinforcement learning, but what happens is you've got to take in the pixel input, and training on images takes a lot of computing power. You can do it, and you need some heavy GPUs. But with the cartpole problem, even though there's a visual representation of it, the input is actually not in terms of pixels. It's actually in terms of angular velocities, how long the cart is up, where is the cart up, you know, the angle of the pole. So it's these like non-picture things, right? Which is easier and quicker to train than images. So that is something I discovered during this whole process. And all we're going to do is talk about some common approaches. Now, we're going to take the approach of number 1, and maybe later we can do some of the other ones. Now, so you've got Q learning and deep Q learning, essentially. It's a value-based method. So we're going to try optimize something called the value function. Now, there's policy gradient methods, right? So there's this so-called acrylic things, and we work on the policy there. So we can go through that in another video, but we're going to sort of dive deep into this. And then you've got these state-of-the-art things here. This proximal policy optimization, which is pretty cool stuff. It's really good. It is actually state-of-the-art. But for now, we're just going to do this because this is a tutorial where we're going to learn about reinforcement learning. Okay, so let's go through the steps. So you've got this Q function, essentially. Now, what it is it contains a state and an action. Sometimes it's called a state action function, and it returns the expected future rewards, essentially. So as we are trying to just approximate this Q function, these Q values, with a neural net. That's the deep Q learning. So what does the training loop look like? Essentially, we observe a state. So we are in a state, right? So let's take our cartpole. We're in a state, and maybe we're like this. We're like this. And now we need to choose an action. So we need to choose left or right. Now, what the epsilon greedy there is it's saying with some epsilon probability, you would take a random action, and the 1 minus epsilon probability, you take the best action essentially. Then you either take a random action or take the best action you've trained on so far, right? And now what we're going to do is we're going to take an action, and then we're going to observe reward and go to the next state. So we take an action maybe like this, and then so if it's like this, we shift it that way, and the pole would sort of come a bit more upright, right? Yeah. And we'll get a reward. We'll get a +1 at that time step because the pole is still upright. And then this is our next state for the next timestamp. And then here's some nitty gritties of the algorithm. We'll store the experience in a replay buffer, and then sample, a sample batch and update the queue network. So given the reward, we'll apply the algorithm and do all that stuff, and then update like, okay, so if it was leaning this way and we took this action, that was good. So that's what that is. Anyway, let's so we'll skip that, the policy stuff. Now there's this is the exploitation dilemma, right? So what this is telling us is that if you want to exploit best known actions, right, you'll always stay stuck. Sort of, maybe you haven't quite found the best policy yet, and you're always just going to stay stuck. So what we want to do from time to time is go explore, take random actions, and that's the whole epsilon greedy stuff, right? So common strategies, epsilon greedy. So you take a few random actions, but you also do a lot of exploiting, and then a soft max, when you're doing a neural network, and just decay schedules, which okay, so the training progression. So what it kind of looks like, right? So episode. So an episode is sort of you go till failure essentially. So that could either you reach the maximum timestamp or the pole just falls down, right? So the random phase, at first you want to sort of just do a lot of random stuff. And then the learning phase, it starts to improve. And then eventually, once you've sort of gotten to a point where things are improving, you want to get something consistent and really start, like the algorithm will start optimizing very quickly. Okay, so I think this is all extension stuff. I think I've been talking for quite some time. Should we get straight to the code? Yes, and here's some resources here. So what I did was I used stable baselines 3 to solve this, and the gymnasium environment to set this up. Okay, cool. Questions? Have you got any questions? Put them in the comments, please. So what we're going to do is go straight to the code. Now, so essentially what we're going to do is we're going to train here. So let's go to, where is it? Carts. Yes. So what we can do is, here we go. So we essentially load the cartpole environment here, and then we essentially, this is how it works. You say, okay, how many episodes do you want to train over? And then is the state terminated or truncated? So I'm just going to go through this quickly. If you're actually really interested in this, there's going to be more on my school community. So I'm just going to give you like some very high overlevel stuff. But if you really want to get into the nitty gritty, join the school community. And what it's going to do, and this school community is about teaching you to become a very dangerous, competent coder, right? But I'm just going to sort of gloss through a lot of this stuff here. So what we're going to do is just, so this is the training loop. And while not terminated, we're going to, so this is the evaluation of the model, right? So let's go to the training one. So here we go. So we're going to load, so we're going to use some pre-trained models here, something I've trained before. We're going to load it in here, right? We're going to load the model, and then we're going to define checkpoints, right? While we're training. So while we're training, because essentially we want to be checking, like we want to have these checkpoints in case our computer crashes and we lose all our progress. And essentially we have put these checkpoints in here. So these are all the steps, and we save it at every 10,000 steps, it looks like. There we go. So those are checkpoint files we can just kind of load back into our model and evaluate it, essentially. Now, it's really easy with stable baselines here, and you see we define the checkpoints here. It's really easy with stable baselines, right? So what we do is we say, okay, how many time steps, log intervals. Oh, okay, so yeah, it's actually every 1,000. My bad. And then yes, and then we just hit learn, and then it starts in this training loop, right? And what we can do after it trains, it'll spit out the zip file here, and we can sort of test: does this work? Is this actually working? So what we're going to do is I'm going to show you something in the middle of training, an example in the middle of training, so something not quite optimized, and then I'm going to show you the optimized version and what that really looks like. So here we go. So we're going to go Python evaluate models. So what's in Python evaluate model? So this is the optimized one here. We'll show that later. And this is sort of the unoptimized one that's kind of struggling. And I just want to show you that to see the progression. Okay, so here we go. So what it's going to do is it's going to run, and this little Pygame window is going to come up. Now you see it's running, and every time it just goes, it ends, right? That means the episode ends, and that was bad. And you see these rewards here, they're not good. They're only 51, 52 or something like that. Remember, the max reward we're aiming for is 500. We're aiming for 500. So let's bring our little cartpole back, and so you see the angle here. It's really struggling. It just keeps falling off, falling down, falling down, falling down, right? So you can clearly see it is unoptimized, right? Now, what we're going to do is we're going to train it for longer. So what I did was I put this on Colab, and then Colab has like a free GPU, and I trained it for 30 minutes, and then we ended up with something a little bit more optimized. So we're going to show you that right now, right? I'm going to show you that right now. And so sometimes you just need to train it for a little bit longer. So we're going to take this model, we're going to comment it out, right? And we're going to load that model there. Now we will run it. So we're evaluating it on the optimized one. And this is what it's going to look like. So see, it almost fell down, then the cartpole, it rescued it. Now it's going to run out of timestamps. You see, length 500, which is the max. So that means we didn't actually make the cartpole fall. And you see, it's just balancing optimally. And it looks like, just being human, that it's sort of right at the start, it sort of is all crazy, and then it has to quickly catch it. So it goes like this. It's like, oh, quickly catches it. And then to make it stay upright, it does these quick ones here. And so I can say we've actually solved the cartpole problem here, because we've reached the maximum reward. Okay, so that is the end of that. That's sort of an introduction to reinforcement learning. Now, if this is your kind of thing, now I have a community, and what this community is about is learning for learning, right? It's going to teach you how to become dangerous. Now, essentially, I really didn't know reinforcement learning. I sort of have, I went to uni and did a bit of math, but I really didn't know reinforcement learning, and I managed to teach myself this in a weekend, and using a combination of AI and just reading and just being very efficient with my learning, I managed to solve this cartpole problem here, which is actually a very valuable skill. You really want to know how to learn things very, very, very rapidly, or learn things rapidly enough, get a good grasp of it, and then know when to delegate things to AI and know when to solve things on your own. And that is essentially what we are going to be teaching in this school community. So we have, the expert coder course, the bootcamp here, and essentially we're going to be making sure we're integrating ourselves with the AI and solving problems all day, every day. And also we have mindset courses as well, how to get rid of your phone from, distracting you and things like that. And the coding mindset course, which is great. So you develop the iron mind when you're trying to code or solve difficult problems. Okay, so that's enough from me. Please do sign up for the school community. There is a free tier, so I hope to see you there, and I will see you in the next one.